Students, good morning. Today I am going to discuss about the changes in entropy of an ideal gas. Entropy changes in an ideal gas. For this discussion, let us consider one mole of an ideal gas. Let us consider 1 mole of an ideal gas. It is trapped in a piston cylinder arrangement. Subject to the condition, this piston is 100% frictionless and movable piston. 100% frictionless and movable piston. In this system, 1 mole of an ideal gas is taken for consideration. Okay. Since the piston is 100% frictionless, also it is a movable one, it indicates pressure inside the system. That means pressure of the gas inside the system is equal to pressure of the surroundings. Hence pressure is constant. Changes in pressure is equal to 0. Okay. Now the first law of thermodynamics. First law of thermodynamics says that the differential properties, relationship between the differential properties, internal energy, heat content and work done. When pressure is constant, the gas is allowed to expand reversibly from a volume V1 to V2. From a volume V1 to V2, listen. The gas is now allowed to expand reversibly. Reversibly means whatever the amount of work done by the system, it is used for expansion purpose completely. Hence it is called as reversible expansion. Now the gas is allowed to expand reversibly from a volume V1 to V2. The amount of work done is equal to dW is equal to P into dV. Okay, it is P into dV. From the second law of thermodynamics, the mathematical representation of second law of thermodynamics is changes in entropy is nothing but dQ by T. Hence, I am going to put this equation here. Clear? Put this equation here. So dQ is equal to du plus dW. du is nothing but C into dt. dW is nothing but P into dV. In order to bring Ts by T, I am going to divide the entire equation by temperature. So dQ by T is nothing but changes in entropy. ds is equal to Cv into 1 by T into dt plus listen P divided by T. For an ideal gas, PV is equal to R into T. P by T is nothing but R divided by V. Hence, instead of P by T, I am going to write like this R by V. So R into 1 by V into dV. In differential form, ds is equal to or del S is equal to integral limit tends to S1 to S2 is equal to dV ln T2 divided by T1 plus R ln V2 divided by V1, or I can write like this del S is equal to CV ln T2 divided by T1 plus R into ln V2 by V1. Clear? Instead of CV, I am going to write the similar equation in terms of Cp like this. Cp minus Cv is equal to R. So Cp minus R is equal to Cv. Instead of Cv, I am going to substitute Cp minus R in this equation. So changes in entropy of an ideal gas is equal to, instead of Cv, Cp minus R into ln T2 divided by T1 plus R into ln V2 divided by V1. Clear? So expand this. Changes in entropy Cp into ln T2 by T1 minus R ln T2 divided by T1 plus R. Instead of R, this value V2 by V1. P1 V1 by T1 is equal to P2 V2 divided by T2. I am in need of V2 by V1. I am in need of V2 by V1. So V2 by V1 is equal to V2 divided by V1 is equal to P1 by P2 into T1 by T2. Substitute this equation here. So R into ln P1 by P2 plus R ln T1 by T2. Clear? I'm sorry. V2 by V1 is equal to P1 by P2 into T2 by T1. T2 divided by T1. Here T2 divided by T1. This term and this term gets cancelled. This is minus, this is plus. Hence the final equation in terms of Cp ln T2 by T1 plus R ln P1 by P2. Clear? This is the changes in entropy of an ideal gas. Using these two equations, I am going to apply three cases. Okay. First case 1, an isothermal condition. Case 1, isothermal condition. P is equal to constant and changes in temperature is equal to 0. Substitute this in this equation. So changes in entropy of an ideal gas. When temperature is constant, this term gets cancelled. Remaining thing is R into ln V2 by V1. That is equal to, when temperature is constant, R ln P1 by P2. R ln P1 by P2. R ln P1 by P2. This is the first case. Second case, pressure is constant. Case 2, isobaric process. P is equal to constant and changes in pressure is equal to 0. Apply this case on both equations. When pressure is constant, what happened? This term gets cancelled. ds is equal to Cp ln T2 divided by T1. Similarly, case 3, isochoric process. That means volume is constant. V is equal to constant and changes in volume is equal to 0. Apply this case here. So changes in entropy of an ideal gas, Cv into ln T2 divided by T1. Clear? Thank you.